Every year, as temperatures drop and snow begins to fall, it's easy to assume that Earth is simply drifting further away from our heat source. The logic feels sound. If you move closer to a fire, you get warmer. But that intuition is completely backward. In reality, Earth reaches its closest point to the Sun, a position called perihelion, in early January, right in the middle of the freezing northern hemisphere winter. So proximity isn't the thermostat. The vast climate shifts we experience every few months are a product of planetary geometry. To understand why a summer afternoon feels so different from a winter morning, we have to ignore how close we are to the Sun, and instead look at exactly how its light strikes the surface of our planet. This model shows Earth's permanent orbital posture. As our planet travels around the Sun, it doesn't sit perfectly straight up and down. It leans at a strict angle of 23.5 degrees relative to its flat orbital path. Because of that permanent lean, the two hemispheres receive light differently. For half the year, the northern hemisphere tilts towards the Sun, taking those solar rays almost dead on, while the southern hemisphere leans away, catching the light at a much shallower, glancing angle. When sunlight hits the ground directly, all of its heat and energy is concentrated into a tight, intense circle. But when that exact same beam of light strikes at a shallow angle, its energy dissipates over a much larger, stretched-out surface area. It is simply the angle of that incoming light, created by our 23.5-degree lean, that dictates how much heat the ground actually absorbs. That physical angle is the geometric engine driving every seasonal change we experience. As Earth completes its annual circuit, this constant tilt creates 4 distinct milestones, crossover events that quietly rearrange global daylight and divide our year. We see 2 points here, the equinoxes. These are the exact moments the Sun crosses the celestial equator, meaning equal night. The boundary between daylight and darkness splits the planet perfectly, leaving day and night roughly equal. In between those equinoxes sit the solstices, occurring in June and December. If we translate the Latin again, solstice literally means sun stopped. From our perspective on the surface, the Sun appears to pause its migration in the sky. This happens when the direct rays hit their absolute geographic limits, 23.5 degrees north at the Tropic of Cancer and 23.5 degrees south at the Tropic of Capricorn. The physical impact of this geometry is easily measured. On a summer solstice in the mid-latitudes, a noon shadow shrinks to its minimum length, and the Sun stays up for roughly 16 hours. 6 months later, that exact same location gets barely 8 hours of light. These 4 crossover points form the hard boundaries of our annual climate cycle. They dictate growing seasons, weather patterns, and the rhythm of human agriculture. But a single year is a microscopic fraction of Earth's history. If we zoom out from a 365-day calendar to a timeline of hundreds of thousands of years, we find that our planetary geometry is not completely static. Over deep time, the actual shape of Earth's orbit, its eccentricity, stretches and compresses. At the same time, the degree of our axial tilt slowly wobbles. These interacting shifts are known as Milankovitch cycles. These orbital shifts operate on a scale of millennia, altering the total amount and geographic distribution of solar energy reaching the planet's surface. We know these deep time cycles exist because we have hard physical evidence. Scientists retrieve ancient ice cores from deep within Antarctica and Greenland, pulling up frozen layers that have survived for hundreds of thousands of years. The trapped gases and isotopes preserved inside these cylinders give us a physical record of the atmosphere. When analyzed, the data shows a direct alignment. Specific shifts in our orbital geometry perfectly match the timing of ancient glacial and interglacial periods. Whether we are tracking the familial arrival of spring in a local garden or mapping the onset of a global ice age, the mechanism remains the same. Our climate is a masterpiece of planetary geometry.